Hi everyone. The topic of the paper I'm going to present is a deep learning approach to diabetes diagnosis. Diabetes is a chronic disease characterized by persistently high blood glucose levels. It adversely affects the heart, blood vessels, eyes, kidneys, and nerves, doubling the risk of vascular disorders in individuals with diabetes. Evidence suggests a strong association between diabetes and certain malignancies such as liver cancer and other non-vascular illnesses. By the end of 2019, diabetes became the 9th leading cause of death, rising by 70% since 2000. With an 80% increase in male fatalities. Diabetes directly caused 1.5 million deaths worldwide, 48% before the age of 70. Currently, 37.3 million people in the US, or 11.3% of the population, have diabetes, with 8.5 million undiagnosed individuals. Currently, the majority of methods for predicting and diagnosing diabetes still rely on blood glucose level measurement. 40. Specifically, invasive blood glucose laboratory tests and glucometers are standard solutions for glucose monitoring at hospitals and homes, respectively. 23. Although these methods can provide relatively accurate test results, some evident disadvantages, such as stringent demand for skills and types of equipment, prohibitive costs, time-consuming, and the pain associated with testing, cannot be ignored. In comparison, machine learning and deep learning-based diabetes diagnosis gather data from real-world datasets, which does not require special instruments and has the advantages of low cost and high efficiency. Some machine learning methods have been proposed for diabetes prediction and achieved some encouraging progress with some datasets such as PIMA diabetes dataset. For example, Brio implemented a data mining algorithm, rough sets with the standard or tuned voting method on PIMA diabetes dataset, which achieved 73.8% of accuracy. Christabel implemented a new class-wise k-nearest neighbor algorithm for the prediction of diabetes, which achieved an accuracy of 78.16%. Palat developed a classification model on PIMA dataset using generalized discriminant analysis combined least square support vector machine, and they achieved 79.16% of accuracy. Smith had proposed ADAP learning, an early neural network model, and achieved 76% of accuracy. Kyra designed a model based on general regression neural network, GRNN, and archived 80.21% of accuracy. Kumar developed a classification model based on multi-layer feed-forward neural networks, and archived 81.73% of accuracy. Ahmed designed a method based on an improved genetic algorithm and a multi-layer perceptron. The model they developed obtained accuracy of 80.4% on the PIMA dataset. Our method introduced the following three main contributions. First, we improved the sensitivity through implementing undersample balancing in the procedure of data pre-processing. Second, we proposed a deep learning model based on backpropagation neural network for diabetes diagnosis. Specifically, by updating losses and biases through backward propagation, the accuracy of samples that are difficult to classify in some datasets has also been improved substantially. Third, we conduct experiments on 4 distinct real-world datasets with different features and Dimensions. The horizontal comparison of the results indicates the superior performance of BPNN in terms of accuracy, among other approaches. We use the following datasets to evaluate our methods. The most commonly used dataset is the PIMA diabetes dataset carried out by the U.S. National Institute of Diabetes and Digestive and Kidney Diseases and available at the University of California, Irvine Machine Learning Repository. There are other well-known datasets that can be used in diabetes diagnosis, such as CDCBR-FSS 2015 Diabetes Health Indicators Dataset and BIT-Mesra Diabetes Dataset 2019. When one class dominates the other classes in a dataset relative to the target class variable, the dataset is said to be imbalanced. However, classification algorithms are designed to assume that the dataset is balanced. When a classifier is trained using an imbalanced dataset, it will probably be biased towards the majority class, which means that the performance of the classifier will be better at predicting the majority class than the minority class. To address this class imbalance, we applied a data undersampling technique. Undersample is a technique that balances the dataset by randomly reducing the size of the majority class until reaching the size of the minority class, despite it might discard some samples from the original dataset. It will not introduce any bias to training and is considered to be one of the most widely used data balancing methods. It is well known that most machine learning methods evaluate the data distance or similarity to make inferences and predictions. However, few features are measured on the same scale. Specifically, the majority of the features are either different in magnitudes or different in units. Hence, scaling the data will bring every feature the same contribution to the classification, which will enhance the performance of classification algorithms. We used standardization as our scaling method since it does not harm the position of outliers, wherein the normalization captures all the data in a certain range. The figure displays the feature distributions for diabetes diagnosis in the dataset before and after scaling using standardization. Standardization has successfully transformed the features to a comparable magnitude, resulting in a more uniform distribution, facilitating the training process and enhancing the performance of the back-propagated diabetes diagnosis model. After data balancing and data scaling, we used a backpropagation neural network as the backbone of our diabetes prediction model. We chose a backpropagation neural network due to its superior representation and feature extraction capabilities compared to other statistical machine learning methods. The BP algorithm works by iteratively updating the network's weights and biases based on the error between the predicted outputs and the actual targets from a set of training examples. The algorithm starts with a feed-forward to compute the activations of each neuron in the network, and then calculates the output error. It then propagates this error backward through the layers, computing the errors for each neuron in each layer. Finally, the gradients of the cost function with respect to the weights and biases are computed using the errors, which are used to update the weights and biases in the network, thereby improving its ability to diagnose diabetes accurately. We also implement batch normalization to improve the training speed and stability, as well as to mitigate the issue of internal covariate shift, thus enhancing the overall performance of our BPNN for diabetes diagnosis. The network architecture is shown in figure above. which is built up by full connections of an input layer, 3 hidden layers, and an output layer. The input layer possesses the same number of neurons as the features. The number of neurons in the hidden layers is 64, 32, and 16, respectively. Eventually, we have 2 neurons in the output layer referring to the 2 output classes. In the network, each fully connected arrow stands for a feed-forward process. The sigmoid activation function has been implemented for each layer, and the output of each layer has been normalized. We evaluated the effectiveness of proposed BPNN model on PIMA dataset, CDC dataset and BitMesra dataset, and compare it with some statistical learning methods, other deep learning methods, and some existing methods done by related works. And our method has significantly outperformed other well-established methods on these datasets, which shows the deep neural network serves as an effective encoder for feature extraction, contributing to the classifier's superior performance. In conclusion, we introduced an innovative diabetes diagnosis model that leverages the backpropagation neural network in synergy with batch normalization. Our model presents a noteworthy advancement in enhancing the accuracy of diabetes diagnosis across authentic datasets. The substantial performance improvement demonstrated not only surpasses related models but also potentially positions it as a benchmark, signifying its pivotal role in shaping the landscape of diabetes diagnosis. Despite limited dataset size and features, our method showed promising results across multiple datasets for diabetes diagnosis. Moving forward, our future work will involve refining and validating our approach with more comprehensive datasets to enhance its robustness and generalizability. Additionally, we aim to improve our diagnostic approach through data processing refinement and feature engineering.